You literally can't ignore the massive explosion of generative AI applications lately, right? But if you've actually tried putting one of these massive foundation models into production, you know the harsh reality. Making them work in a lab, that's one thing, but serving them efficiently, affordably, and quickly to real users, yeah, that is a completely different beast. That's the wild world of AI engineering. Today, we're unpacking a brilliant breakdown of this exact challenge from Chapter 9 of Chip Huon's book, AI Engineering, Building Applications with Foundation Models. Okay, let's dive into this.
Here's our roadmap for this explainer. First, the inference bottleneck. Second, the 3 levels of optimization. Third, metrics that actually matter. Fourth, crafting a better model. Fifth, beating autoregressive generation. And finally, attention and service tactics.
Moving right into part 1, the inference bottleneck, or identifying the core villains. Think about it like this. To optimize city traffic, planners first have to find the congestion points. The exact same logic applies to an inference server. Before we can speed things up, we have to find out exactly what's slowing us down. Usually, we're dealing with 2 main computational villains. On the one hand, you've got compute-bound tasks. This is where the time it takes to complete a task is dictated entirely by intense mathematical calculations, kind of like heavy password decryption. On the other hand, you have memory bandwidth-bound tasks. These are constrained by how fast data can actually move around inside the system. So if you're storing data in CPU memory but training your model over on the GPUs, well, moving that data back and forth takes precious time. When we optimize, we are constantly fighting one or sometimes both of these bottlenecks. Figuring out which one is choking your system, that dictates literally every step you take next.
That takes us to part 2, 3 levels of optimization and the R-tree metaphor.
So how do we fight back against these bottlenecks? Well, Chip Huon introduces this fantastic overarching framework to ground these highly technical concepts. We can optimize at 3 distinct levels, and she uses an R-tree metaphor, and this brilliantly illustrates the entire optimization stack. Basically, model-level optimization is like crafting better arrows. Hardware-level optimization is like training a stronger and better archer. And service-level optimization? That's like refining the entire shooting process from start to finish. We're going to explore how to craft those better arrows and refine that shooting process today. But first, we need to know how to measure our aim.
Which brings us to part 3, metrics that actually matter, measuring our success.
Before we just start tweaking models and servers, we really need to define what targets we're aiming for. What does success actually look like when you're serving an AI app? Take a look at the stark difference here between raw throughput and goodput. Honestly, a lot of teams just look at raw throughput, how many total requests the server handles per minute. But think about it, if an inference service completes 100 requests a minute, but only 30 of them actually meet your software-level objectives, your raw throughput is totally misleading. Goodput, instead, measures the number of requests per second that actually satisfy those crucial user latency objectives. I'm talking specifically about TTFT, which is time to first token, and TPOT, time per output token. Processing massive volumes simply doesn't matter if it just results in a laggy, frustrating user experience. We also have to measure how efficiently we're using our extremely expensive hardware, right? We have MFU, or model flops/utilization, which measures how many operations your hardware is actually doing compared to its theoretical peak. Then there's MBU, model bandwidth utilization, measuring the percentage of achievable memory bandwidth that's actually being used. Interestingly, compute-bound workloads usually show a higher MFU, while bandwidth-bound workloads generally hit a higher MBU. If you're paying for massive GPU power, you want these utilization numbers as high as humanly possible. Let's shift gears and see how this builds into those micro-level optimizations.
Part 4. Crafting a better model, looking at size and architecture.
We're moving down to the model level now, really focusing on improving the arrows in our R-tree metaphor. The golden rule here? Making a model smaller almost always makes it faster. 2 of the absolute most powerful techniques for model compression are quantization and pruning. Quantization is incredibly popular right now. It basically involves reducing the precision of a model, say dropping from 32-bit to 16-bit. That instantly cuts its memory footprint in half and boosts throughput. It's a real game changer. Pruning, on the other hand, comes from the realization that a massive model might just contain a smaller subset of parameters that capture the whole thing's behavior. You can literally remove entire nodes, which fundamentally changes the architecture, or you can just find the least useful parameters and set them to 0, creating sparsity. Both of these techniques shrink the model to boost speed, ideally without destroying the quality of the actual output.
Next up is Part 5, beating autoregressive generation with decoding tricks.
Now, even if you have a perfectly compressed model, we still run headfirst into a very painful reality, the autoregressive decoding bottleneck. These language models generate text one single token at a time, sequentially. Now, what's really interesting about this slide is that massive 100 right in the center. In an experiment, Andy-Scale found that a single output token can have the exact same impact on overall latency as 100 input tokens. Because output tokens have to be generated sequentially, it is just an incredibly slow and expensive process. In fact, output tokens actually cost about 2 to 4 times as much as input tokens across most model API providers. So, how do we beat this?
Well, one super clever technique is speculative decoding. Instead of forcing your massive target model to generate every single word from scratch, you use a much smaller, faster draft model to quickly propose a sequence of tokens. Then, your giant target model just verifies them in one go. Because verification is highly parallelizable and way faster than generation, this drafting technique completely bypasses the autoregressive bottleneck. It can often cut response latency by more than half, and the best part? It doesn't sacrifice a single drop of the target model's quality.
Another brilliant trick is inference with reference. Think about use cases where you're asking a question about a long uploaded document, or maybe asking a model to fix a bug in a snippet of code. The model often just repeats large chunks of the input verbatim. So instead of painstakingly generating those repeated tokens one by one, inference with reference just identifies the relevant text spans from the input context and directly copies them over. It doesn't even require an extra draft model, and it works absolute wonders for lossless acceleration in specific scenarios where the inputs and outputs heavily overlap. Finally, Part 6, Attention and Service Tactics, or Fixing the Bow and Archer. We really have to talk about the massive memory drain of the attention mechanism and the service-level tactics that actually tie all of this together in the real world. The attention mechanism in transformer models requires something called a KV cache. This stores key-value pairs, so the model doesn't have to repeat redundant computations. But the memory requirement for this cache is, well, it's staggering. To put it into perspective, for a Llama 2 7B model, with a batch size of 512 and a context length of 2048, the KV cache totals 3 terabytes. Let that sink in. That is 3 times the size of the model's actual weights. This sheer scale creates a severe hardware bottleneck, especially when you're dealing with long context applications. So the crucial point is that developers are actively fighting this KV cache bloat. The strategies for this generally fall into 3 distinct buckets. First, fundamentally redesigning the attention mechanism itself. Second, optimizing the KV cache storage, maybe using quantization or adaptive compression. And third, writing highly efficient, hardware-specific code, these are known as kernels, to make the actual attention computation run faster on the very specific chips being used. And overseeing all of this is the service-level optimization, the refined shooting process from our archery metaphor earlier. The inference service manages resources dynamically. Instead of basic, old-school batching, modern services use continuous batching. They inject new requests into the batch the exact moment one finishes, which drastically reduces idle time. They also decouple the prefill and decode phases, basically processing that heavy initial prompt completely separately from the sequential token generation. And to scale up, they rely on tensor parallelism, which splits the computation of a single model across multiple GPUs to reduce latency and serve larger models. That's alongside replica parallelism to handle higher traffic. These techniques aren't modifying the models themselves, they're just perfectly orchestrating how the hardware resources are allocated.
The pace of innovation in AI engineering right now is just relentless. The techniques used to squeeze every last drop of performance out of these models are evolving daily, which leaves us with a really fascinating question to ponder. Will the next great leap in generative AI come from researchers inventing entirely new, non-autoregressive architectures that bypass these bottlenecks altogether? Or will it come from AI engineers just perfectly optimizing the archer, the bow, and the arrows we already have? It is a thrilling space to watch, and understanding these inference optimizations gives you a front-row seat to the future of AI. Thanks so much for exploring this with me.